So all of you are well prepared for the upcoming test on Sunday, I hope. Okay. So we'll talk about the test also as we go along today. Now, yes, Dhruv, you had a doubt from some question in the previous class.
Yes, sir. So that we integrated e to the power minus x1. That
E raised power minus x integration. Okay, I'll explain. Okay. So we'll go over the basics of integration once more, and I'll explain that question. We'll do that. Okay. Okay, so we had seen two types of integration last time: indefinite integration and definite integration. So there was the whole concept of antiderivative. Okay. So the basic formula being this: for n not equal to -1, whereas for n equal to -1, we had the integration ln x plus c. And then we had all the trigonometric and exponential formula, etc. Okay. Properties, trigonometric formula. And we also had the exponential one, e raised power x dx. Then we had discussed about the substitution, the basic type of substitution. So the basic type of substitution we had seen when we have a linear term. So the idea was this, that if we know integration of fx is this, then integration of f of a linear term becomes 1 upon a times the indefinite integral of that linear term. So this was the idea. So this came by substituting that linear term as something different, okay, as some substituted variable or as a dummy variable. So this is an example of that only, e raised power minus x. So we just want to find the indefinite integration of e raised power minus x. Now we can see that we know integration of e raised power x is e raised power x plus c. So what about integration of e raised power any linear term like this? It will become 1 by a e raised power same linear term. Right? This is clear now, Dhruv?
yes, sir.
Okay. So here minus x is a linear term. No? It's like a is equal to -1 and b is equal to 0. So you can see that if you directly go by that substitution method, it becomes e raised power minus x divided by -1. So that's minus e raised power c. Got it now?
Yes, sir. Okay.
Okay. Moreover, now you can see if you differentiate this, you will get this. Okay. If you want to do all the steps properly, what you can see here is that you substitute minus x as z. So when you substitute this, dz by dx is equal to -1. So that means I should substitute dx as minus of dz. So the integration becomes e raised power z but into minus dz. So it becomes minus of e raised power z plus c, and that is equal to minus of e raised power minus x plus c. So that is the proper step-by-step method of it. But for linear functions, we don't need to apply the steps always. we can just apply this direct formula. I mean, for linear substitutions, we can apply this direct formula. Okay, so hope this is clear, Dhruv.
Yes, sir. Clear.
Okay, so let's see some more examples of this. So I'll come to integration with limits also, but now one important set of manipulations is making use of the formula of trigonometric identities. Sine 2x is 2 sine x cos x, and also that cos 2x can be written as cos square x minus 1 or 1 minus 2 sine square x. Okay, so this is very useful because from this we can always write sine x cos x as this. Okay, and this is very useful because from this we can write cos square x as 1 plus cos 2x divided by 2, and sine square x as 1 minus cos 2x divided by 2. So these identities on their own become very important because they can be used in integration now. So we'll see how to use them in integration next. So next we'll see that. So if I have integration of sine x cos x, that can be now written as integration of sine 2x by 2. So that is 1 by 2 comes outside, integration of sine 2x dx. Okay, and now I can make use of the fact that integration of sine x is minus cos x. So therefore integration of sine of a linear term will become minus 1 by a cos of that same linear term. So this can be used here now. This can be used here. So this will become minus 1 by 4 cos of 2x plus c. So integration of sine x cos x. So just write this down, then we'll come to the use of these two also.
But there's nothing like the product rule or quotient rule, right, for integration?
No, there is the product rule is a different thing in integration actually. It's something called integration by parts. Okay, which is a little bit more complicated. We will not be doing integration by parts as part of basic calculus. It will be then advanced calculus. Here actually the product of sine and cos is being reduced to a simple sine 2x term using a trigonometric identity. You're understanding better?
Yes, sir.
Sir, can you explain the last two steps again?
These steps over here.
Yes, sir, the below two ones.
So this is of course this is integration of sine x cos x only. The left hand side is the original integration. The right hand side, what we've done is we've integrated sine 2x using this formula. That integration of sine x is minus cos x. So integration of sine of a linear term will become minus 1 by a cos of that linear term plus c. Simple substitution.
Okay, sir.
Okay. So here that ax plus b is 2x. No? So a is 2 and b is 0. So it will become like this. Understood now?
Yes, sir.
Okay. You can always check your answer, okay, by doing the differentiation. Okay, so we can check that differentiation of this term, whether it gives you sin x cos x or not. And you can see it does give you, because differentiation of cos is minus sine, but you'll have to again use chain rule because it's cos of 2x. So you can see you get sine 2x by 2, which is basically sin x cos x.
Sir, is there any other method to do this? Means instead of substituting sin x cos x as sin 2x, other than
There is,
that.
there is another method also, and we'll come to that also. Okay, but the direct method you should remember for this kind of integration is this one, because the other method is a bit lengthier. Okay,
Yes.
the other method is making use of the fact that cos is the derivative of sine.
Yes.
Okay, so it's a slightly more lengthy kind of substitution. Okay, so now similarly, if we have the integration of cos square x, then what we have to do here is we have to express it as 1 plus cos 2x divided by 2, like this. Okay, so then this breaks into two integrals. So this becomes x by 2, okay, plus this becomes sine 2x by 4 plus c. And you can again check that if you differentiate this, if you differentiate the antiderivative, you should get the original function. So this is just a simple way to check that the answer we have got does not have any error. So you don't need to memorize these formulae of integration cos square x or sine square x or integration sin x cos x. You just need to keep in mind that when we are integrating these, we use these identities. Okay. The identity of cos 2x and sin 2x from trigonometry. Because again, these are integrations which are going to be pretty common in physics later. Okay, so likewise, you can see that the integration of sine square x, very similar process, but sine square x is 1 minus cos 2x by 2. Comes this.
So in the first one, cos square dx, it should come only 1 by 2, no? Why x by 2?
No, integration of dx is x, na beta. Remember, integration of a linear term, sorry, of a constant is this, no?
Acha, हाँ, yes, yes.
So now using these integrations, we will see an interesting fact about the function sine square x and the function cos square x. If you look at the graph of sine square x, for example, see that it looks like this kind of a varies between +1 and 0. And similarly, if you compare this with the graph of cos square x, so sine square x actually has a cycle of pi. This is also a periodic function. It has a cycle of pi. And as you can see from the graph, it varies between 0 and 1. Okay, whereas cos square x does the same thing, but this manner. In fact, their graphs are interrelated in such a way that if you superimpose their graphs, okay, then you can see why their sum is a constant. Sine square x plus cos square x is equal to unity. So you'll see that interesting fact if you draw the graphs. This is the sine square x graph. If you superimpose that with the cos square x graph, you see why their sum is always equal to unity. For example, at pi by 4, they are both equal to half. But at pi by 2, one is sine square is 1, cos square is 0. Okay. And again at 3 pi by 4, they are actually equal to half. Anyhow, so if I want to find the area under the graph of sine square x from x equal to 0 to pi, x equal to 0 to 2 pi, and then I want to repeat that cos square x. Same. Okay. Okay, just work it out, these two. So from the symmetry, what you should expect is that whatever we are getting for the A part, the B part should be exactly double of that, because it's 2 cycles. So in the A part, whatever area you are getting is like this shaded portion. In the B part, it should be double of this. So it should be this. Okay. You can just verify that by the integration. Just work this out and tell me how much you are getting for these two. Yeah, people not got the answers for this yet. So the area under the curves comes from integration with the limits. So as you know that if we have any function and we want to find the area under the curve between the points A and B. So this area comes by this, okay. So just put the limits on the indefinite integration. Is the value of the indefinite or the antiderivative at B minus the value of the antiderivative at A. So this quantity is actually the area. So let's apply that now to this. So in this A part, talking about the sine square function, this sort of function, but I want to calculate the area between 0 and pi. So I want to calculate this area. This area will become integration of sine square x, but with the limits x equal to 0 to x equal to pi. So now to complete this integration, we will use that trick, that sine square can be written as 1 minus cos 2x by 2 from 0 to pi. Okay, the constant term can be left out because anyway it will cancel out. So you can see you'll get the area as pi by 2. Very good, that's correct. Ibrahim, that's correct.
So what did you do in the second last step?
In this step, we have substituted the limits. So see, basically, what we have done up to this step here, this is this step over here, is the indefinite integration. On that, we are putting the limit 0 to pi. So this is the value of the indefinite function at the upper limit b, which is pi, and this is the value at the lower limit, which is 0. Okay.
Got
So
it.
so if I just elaborate that a little, can add some steps here.
No, sir, I got it.
Understood? Okay.
Yes, sir.
So basically, this will become, this function at the upper limit will become pi by 2 minus sine of 2x. So that is 2 pi divided by 4 plus c minus 0 minus sine 0 plus c. So that's how it becomes Okay, now likewise, what we expect from the graph and the symmetry is that this area between pi and 2 pi should also be the same. Okay. So what we expect is that it should be equal to this from pi to 2 pi, which is pi by 2. So therefore 0 to 2 pi just become double of this, should become pi. And that is what we'll get when we do the integration. I mean, when we put the limits again.
Sir, but the area should come in units, no? Why is it coming in pi and pi by 2?
Now the thing is, see, here we are just treating it like a mathematical function. So on the x-axis, we have, angle in radians, which is dimensionless, right? And on the y-axis also, we are having 0 to 1, which is dimensionless. Okay. So the area is also coming as a dimensionless quantity. You're understanding the point?
Yes, sir.
Okay. But suppose, we had, okay, I'll explain that in another question. Okay. Because when we write the function sine square x, the quantity x has to be dimensionless because it's an angle. No?
Yes.
But if we put some coefficients, then we can see that we can make the quantity x have some dimension, like length or time or something like that. And if we put some coefficient to sine square x, then we can make the quantity y also having some dimensions. Okay. So we'll discuss about that. Yes. Okay, so this B part is also clear to everyone, I hope, from this.
Yes, sir.
So whether you go by this symmetry method or you actually redo the question using this substitution. So repeat all these steps, okay, and you will come to this new area from 0 to 2 pi, come out to be pi, which basically again, verifies the symmetry of the graph. That is, second cycle is identical to the first cycle. Now you will see another interesting thing. Not only the second cycle is identical to the first cycle, but if you break it from 0 to pi by 2, and then again pi by 2 to pi, again these two halves are mirror images of each other. So the areas will also be half. So if you were to do the integration of sine square x from 0 to pi by 2, you would get pi by 4 as your answer. So this would actually be integration pi by 2 to pi. And this would actually be pi by 4, both these values. So now you'll see the cos square x graph has the same shape exactly. It's just that it is shifted.
Sir,
Yes.
so for when we were doing differentiation and we had to find a distance traveled, so that's also area under graph. So when we do differentiation of that, and then if you're seeing it here, the antiderivative is also the area under. So
Yes.
then can you explain that?
Antiderivative with the limits beta is the area under the curve. The antiderivative is indefinite integration, but for area we have to do definite integration. We have to substitute the limits now.
Yes, sir.
Okay.
So can you explain how both are giving area?
No, come again. In what we are getting the area in differentiation?
In differentiation, if you find the distance, then that's basically the distance under the area under the graph, right?
But area under which graph? Beta? Velocity time graph, no? Or speed versus
Yes,
time
sir.
graph? Okay, so what is the relationship over there? Speed is the rate of change of distance now. So therefore, distance,
Okay, sir.
got it now? So it's the reverse operation. No? So it
Okay,
is like,
sir.
see, if I know distance as a function of time, okay, then speed becomes what? It becomes derivative of that function. So that means now what is the relationship between this function and this function? This is anti-derivative. Because the relation between
Oh,
this and
okay, sir.
this is derivative.
Yes, sir.
So, remember we had done those type of questions that speed as a function of time is suppose given to us something linear like 2t plus 3. And I said that find distance as a function of time. If you go back to worksheet 2 and 3, we had done some questions like this by sort of guesswork. We had said that speed is ds by dt. And here that is a linear function. It's a linear function. So that means s must be what kind of a function? It must be a quadratic function. Okay. So we assume
Yes,
that s is equal to some at square plus bt plus c. Okay. And then we went about finding these coefficients a, b, c. So we said that, okay, s at t equal to 0 must be 0. So that means c is equal to 0. And ds by dt will become differentiation of this term, at square plus bt. And that should be equal to here 2t plus 3. So by comparing the two sides, what we got is that 2at plus bt is equal to 2t, sorry, plus b is equal to 2t plus 3. Okay. So we compared the two sides and we saw that, okay, 2a is equal to 2. That means a is equal to 1 and b is equal to 3. So now from this we got that, okay, s as a function of time should become how much? It should become t square
got it,
plus
sir.
3t. Okay. Yeah. So this is how we have done these questions at that stage. But now you can see we can do this question by integration. We don't need to do this guesswork kind of work. Okay. So now we can approach this question using integration. So you can do this question now like this, that b is ds by dt. That means, ds integration is equal to v dt. So 0 to some time t, the distance is changing from 0 to s. So we will substitute this now. So integration of ds will be what? It will be s, and v ke jagah we will substitute the given function, which is 2t plus 3 dt from 0 to t. So s with the limits s equal to 0 to s equal to s. On the right hand side, the integration of 2t is t square, and the integration of 3t is 3t. Okay, so this is the indefinite function. I'm not writing the constant, but this has to be substituted from limits t equal to 0 to t equal to t. So we can see on the left hand side, the upper limit is s, the lower limit is 0. On the right hand side, the upper limit is t square plus 3t. And again, the lower limit is 0. So this is showing us that s as a function of time is t square plus 3. Now at this stage, this might seem like a lengthier thing compared to this, but actually when you get used to integration, you'll see that this is a direct one-step process, because we are given v as a function of time, we integrated it. Whereas this was a
Yes,
two-step process because we assumed some value of s based on the fact that your v was linear. Okay. And moreover, if v is a more complicated function, then that guesswork is not so simple. Understanding now, beta?
got it, sir.
Oh. So we will come back to this also. This is like the kinematics type of applications of calculus. Okay.
Sir, could you please scroll up? I was like noting it
Yeah.
down.
Yeah. So before this, yeah, this is what we're discussing. Now we have to come to the B part of this, where we have to show that the cos square graph has a symmetry with respect to the sine square graph, and that symmetry extends to what we're discussing about the area under the curve also. Okay, so just wind this up with the comparison of the two things again. So if you look at the cos square graph, it's like this between 0 and pi. So when we calculate this area, interestingly, it will have to come identical to the area for the sine square graph between 0 to pi. Because of that symmetry. When we compare these two areas, it will have to come out the same, because if you divide this area into these two halves, they're exactly these two halves. Okay. So that is what we can prove by integration here. That cos square x from 0 to pi will be the same as sine square x from 0 to pi. And the reason for that is what I just told you. So when we are putting limits, we need not write the constant in the indefinite integration because it will just cancel out. That just confirms what we are talking about. Okay. And likewise, to calculate 0 to 2 pi cos square x, it will come out to be pi. Yes, so that's correct, Nitish. Okay. Okay, so these are a couple of important integrations to remember. Integration of cos square x, sine square x, and integration of sine x into cos x. Okay. Now we will move on to another type of substitution. So integration by substitution. So now we will see a sort of a equivalent of chain rule. First, we'd seen the substitution of a linear term. Now we will see the equivalent of chain rule in integration. So that is, if we have something like this, okay, then this actually becomes So this might seem like a very complicated thing right now, but I'll explain how this works. Okay. So if we are integrating the product of two functions, one is a composite function and the other is the derivative of the inside term. So I'll just give you an example to understand this. Suppose we are integrating, let's say, square root of 1 plus x square into 2x dx. Now you can see that this function, square root of 1 plus x square, is a composite function. It is f of gx, which is square root of gx, where gx is equal to 1 plus x square. And we can see it is multiplied with this term 2x, which is the derivative of gx. Okay. 2x you can see is g prime x because it is differentiation of 1 plus x square. So that's how this integration this fits this kind of format. It is f of gx into g prime x to derivative of the inside function. Okay. So for this, what we can do is to understand how we get this above formula. We can do this method that we substitute gx as z. So in this case, we substitute gx is which term now? 1 plus x square. So we substitute 1 plus x square is equal to z. This is our dummy variable. Okay. So then differentiate both sides. So you can see 2x is equal to dz by dx. So that means 2x dx can be substituted as dz. So this thing and this thing, substitute them both in the integral. Okay. So our original integral, which was square root of 1 plus x square, whole thing into 2x dx. Now this becomes square root of z into dz, which is a very simple integral. It is z to the power half dz. So it is z to the power half plus 1 upon half plus 1 plus c. So it is 2 by 3 z to the power 3 by 2 plus c. Now resubstitute. So to resubstitute, we put z back as what? Gx. And gx was basically what? 1 plus x square. So this becomes 2 by 3 into 1 plus x square to the power 3 by 2 plus c. So our integration of this whole term has become this. Okay. And the way to check your answer is again that if you differentiate the right hand side, that is the antiderivative, using the chain rule, you will see that you get the integrand or the function that we have integrated, which is this whole thing. Okay. So we'll come back to the fx gx terminology. First, just go through this example, how we have done the substitution from here to here. Okay. And we have come up with this answer. Then we'll go back to the general form of this substitution. So this can be a little bit tricky sometimes because you have to look at the function and you have to be able to identify that there are the two terms in it. That there is the square root of 1 plus x square, where inside the square root we have the term 1 plus x square, and that 1 plus x square's derivative is present outside. That is the 2x is there. The 2x is the derivative of 1 plus x square. So you have to be able to observe this and identify. Okay, which is what makes this kind of substitution a little bit tricky. Okay, and it takes a lot of practice. But for basic calculus, we don't need very tricky questions. We just need some standard examples of this, which we should be able to do, which will come often in physics. Because remember, we are doing integration from a point of view of application in physics. Okay, not from some kind of okay, so just go through the steps of this particular question and tell me if everything is clear. Then we will come back to the general form.
So how did you get 2x is d 1 plus x, 1 plus x derivative?
1 plus x square.
Yes, sir.
Differentiate 1 plus x square, na beta?
Oh, okay, sir. Yes, sir.
We are just differentiating. So it's like, think of it like the opposite. Now I've written 1 plus x square as z. So z is equal to 1 plus x square. So what is dz by dx? It is differentiation of 1 plus x square. No?
Yes, sir.
So after the dummy variable step, that 1 plus x square is z, the next step is we've just differentiated both sides of the equation. The differentiation of left hand side 1 plus x square is equal to differentiation of right hand side, which is dz by dx.
So
Yes.
we did not integrate 2x. We just integrated root of 1 plus x square.
No,
And-
we integrated square root of 1 plus x square into 2x dx beta. So in that 2x dx is getting substituted as dz now.
Uh,
You
okay,
understanding now? Because z is 1 plus x square now.
yes, sir. Okay, sir.
Understood the point? Yeah? Okay.
Yes, sir.
Okay, so having understood the steps, now we come back to the original form of this. Let's observe how this actually comes. Okay. This comes by just applying these same steps that we have done for this particular integration, square root of 1 plus x square into 2x dx, but applying it to this. So here we will be substituting gx as z. So this will become fz dz. So integration of fz is iz plus c, and then resubstitute z as gx. So that is the general method. Okay. So general method here is that if we observe, we have a composite function multiplied by the derivative of the inner term, okay, that we want to integrate. The quantity we want to integrate is a composite function, okay, but not just the composite function. Has to be multiplied with the derivative of the inner term, gx. Then the steps here is we substitute gx as z. That is our dummy variable. So derivative of gx becomes dz by dx. So we can substitute g prime x into dx as dz. So then what happens is our integration of f of gx into g prime x. This becomes actually f of z into dz. And that is the antiderivative of this plus c. And then we resubstitute. So finally we get, so these are the general steps. So here we understand that So let's see another simple example. Suppose we have e raised power sine x into cos x dx. So you can see it is exponential of a function sine x whose derivative is cos x. So you can use this. Okay. So just try this out and tell me the answer. Yes, Ibrahim, that's correct. Aryan, that's correct. Aparna, just go through your steps again. Janvi, that's correct. Okay, so what we can observe over here, that this function e raised power sine x, it is like an f of gx, where gx is sine x, okay, and f is the exponential function. Whereas this function cos x, it is the derivative of sine x. So it is basically g prime. So we can make use of this concept here. This in this integral, we can substitute sine x as z. So cos x is dz by dx, or that whole term cos x into dx can be substituted as dz. So integral e raised power sine x into cos x dx. This sine x becomes substituted as z, and cos x dx becomes substituted as dz, this whole term. So this becomes e raised power z dz. So that becomes a very simple integral. It becomes e raised power z plus c, and then we resubstitute. So it becomes extremely easy, as you can see. It is just a matter of observation, okay, that the term cos x is the derivative of sine x. So we could do this.
Sir, can you please show me the general formula once again?
Yes. So this becomes a general formula.
Sir, according to this formula, the answer to this sum should be minus cos x plus c, no?
क्यों?
Sir,
देखो, what is the function f? The function f is exponential, ना बेटा?
yes.
So what is the antiderivative of exponential? It's exponential only. है ना?
Yes.
And what is gx? It's sin x, na? So this I should be exponential and gx should be what? Sine.
Sir, what is I in this
I
formula?
is the antiderivative of f, na beta? See?
Acha. I thought I is the integral of gx. That's
No, right? I is the antiderivative of the outer function f, na?
yes.
Got it, na? Understood?
Yes, sir.
So let's do some examples of this. Okay, just try out these questions, people. The last one, we'll just change it for now. We will do that one also, which I told you, but little bit lengthier, that one.
Sir, I just remembered one thing. Shome, sir.
Yes, very good, Ibrahim. Aryan, just check your third one's answer once. First and second are good. So in the first one, you can see that if you take this as z, then this term is dz by dx. Similarly, in this, if you take this as z, then you can see that dz by dx is equal to 3x square. So this term is 1/3 of dz by dx. And this, in this, if you can see that if you take sine x as z, then cos x becomes dz by dx. Okay, very good. So now people are getting the answers. Let me just cross verify them. Okay. So let's start with the first one. So I'm not going to use a direct formula. Okay, I'm going to do the substitution properly for each one. And that is what I suggest that you also do with these type of questions. Okay, like I had told you in chain rule, that don't go with the direct formula method initially. Okay, at least initially do all the step-by-step method of substitution and all that. So same way over here. So substitute 1 plus x square as z. So 2x becomes dz by dx. That means 2x dx can be substituted as dz. This is one substitution you do, and this is the other substitution you do. So your integration becomes dz by z, which is ln z plus c. And now you resubstitute. This becomes natural log of 1 plus x square plus c. Because always remember that the integration of this is the exception to the x to the power n rule. Likewise, let's come to the second one. So in this, we substitute this term. So x square into dx can be substituted as 1 by 3 dz. So the integration then numerator becomes 1 by 3 dz, and the denominator becomes square root of z. Okay. So finally, this becomes the integral. So this is just mathematical manipulation. You will get used to this. Okay, now try the third one by the same method. Mansi, your answer is correct. Aryan, your answer is also correct for the third one.
Sir, mine?
What is your answer, beta?
Sir, minus 1 upon sine x plus c.
That's also correct. But there's a minus sign. Check once. There's an added minus sign.
Yes, sir, minus 1 upon sine x.
Minus 1 upon. Yeah. It's correct, beta. All right, so let's wind up the third one. So cos x upon sine square x, it's quite easy actually. You'll see that it becomes a 1 by z square type of integration. Right? Okay, so the integration becomes, the numerator simply becomes dz and the denominator simply becomes z square. Okay, so we use the formula. So this is correct, but you can also reduce it to minus cosec x plus. Now you can see that some of the standard trigonometric formula can be proved by using this. Okay, for example, you have the integration of tan x. You can write that as, and you can see that put cos x as z, then minus sin x is dz by dx. So sin x dx becomes minus of dz. So this becomes minus of dz by z. That is minus ln z plus c. That is minus ln cos x plus c. That is ln of cos x to the power minus 1. That is ln sec x. So what we had seen as a standard formula actually, that integration of tan x is ln sec x, actually comes from substitution.
Sir, sir,
Yes.
sir, I had a doubt in the A part.
Yeah, Shrishita, beta, tell.
Sir, in the substitution part, when we resubstituted, we wrote dz as dx into dz.
No, resubstitution is in the last step, beta. After doing the integration, na, we get the antiderivative in terms of z, na. So z has to be resubstituted as whatever the function gx was. Understood,
Yes,
na?
sir. Yes, sir.
So resubstitution comes after completing the integration, na? So we are getting the antiderivative, in terms of z. So in that antiderivative, we have to resubstitute z as whatever our gx was. So here our gx was sin x. Here our gx is cos x in the tan x one, right?
Yes, sir.
So what about integrating log?
Yeah, that is something more complicated, but that comes from something called integration by parts. Okay, so we will not be doing that right now in our basic calculus portion. Okay.
Okay, sir.
Okay, now, for example, even the other standard trigonometric integrations like integration of sec x. This can be done by substitution, but using this thing, using a manipulation. Okay, and that manipulation is a bit tricky. So what you do is just arbitrarily you multiply this with the term sec x plus tan x divided by the term sec x plus tan x. So our numerator becomes this, and our denominator this. Now you notice that the numerator is the derivative of the denominator. If you take sec x plus tan x as z, then your dz by dx is so this becomes dz by z. So on resubstitution, it becomes. So you can say this is a proof of one way of proving that this is. Of course, last time we had seen the another way of proving this is just differentiate the final antiderivative and you get sec x. So that itself proves. Okay. So similarly, and show why this is ln minus ln cosec x plus cot x, because you just multiply, divide this with cosec x plus cot x. So it's a manipulation, okay, but the manipulation results in this kind of integration. Now you substitute cosec x plus cot x as z. So minus of cosec x cot x becomes dz. Okay, so this integral becomes minus of dz by z, becomes minus ln z plus c. So finally, so this is quite lengthy actually. So you should remember this as a direct formula. You should remember that this integration is the direct formula for this. But this is one way of showing the steps how we come to this antiderivative from this. So in between, there's also a manipulation step involved. Okay, so now another set of integrations which we see quite often in physics type of applications is ones that involve differentiation of trigonometric functions, antiderivative of inverse trigonometric functions. So let's recall inverse trigonometric functions once, and then we will see the integrations related to them. So I told you the chain rule method of differentiating inverse trigonometric functions. So for example, if we had y equal to tan inverse x, we saw that tan y was equal to x. So differentiation of tan y with respect to x became differentiation of this. So it became sec square phi dy by dx equal to 1. So we ultimately got. So from this, what we can also observe is that the differentiation of tan inverse function is equal to 1 upon 1 plus x square. Now what this also means is that the integration of 1 upon 1 plus x square should be equal to tan inverse x plus c. Okay, so this statement actually implies this. If the differentiation of one function is equal to this, then the integration of this function should be equal to, that is a concept of antiderivative. Okay, so let's see how this works out by using substitution also. So first, just note this down. Okay, so now likewise, we also have, for example, for differentiation of sine inverse function, if y was equal to sine inverse x, then how to get dy by dx? So differentiation of sine y is equal to unity. Okay. So cos y into dy by dx is equal to 1. So we had that differentiation of the sine inverse function is given by the formula square root of 1 minus x square. So we invert this now. We can say integration of the right hand side is equal to sine inverse x. So this implies that integration of 1 upon square root 1 minus x square is sine inverse x plus c. So we have these two important formulae now. And we have okay, so these integrations can also be understood in a slightly more manipulative manner. Okay, so example, we have something like this. Where a is a constant. Then what we can do here is we can express this as, so we can divide the numerator and denominator with a square. Okay. So that will make it like this. Okay. So we just divided the numerator and denominator by a square, and then we can substitute x by a as z. Okay. So So this further becomes 1 by A. So that becomes 1 by A tan inverse Z plus C, or it becomes 1 by A tan inverse X by A plus C.
Sir, but there's a root over we forgot.
Which root over?
Sir, in tan, sir, 1 upon z square root over, right?
No, beta. See, this is the tan inverse integration. Dx upon 1 plus x square is tan inverse x.
Oh, sir, I've written everything wrong then.
You just copy this down properly. Differentiation of tan inverse x is 1 upon 1 plus x square. No, beta. So integration of dx upon 1 plus x square is tan inverse x.
And so for sine, there is root over, right?
Yes, for sine there is root over. For sine inverse that is. Okay, now, so these two integrals are clear now. Okay, so similarly, if we have integration of this kind of term, dx upon square root of square root of a square minus x square, where a is a constant. Then again, we can make use of this integration that we know this integration is sine inverse x. Okay, but how we'll make use of is that we have to replace this a square with 1. So to do that, we have to divide the numerator and denominator by 1 by a. We have to divide the numerator and denominator by a. So this can be written as 1 by a dx upon. Now take the 1 by a inside the square root, so it will become 1 by a square. So it will become 1 minus x by a whole square. Okay. And then substitute x by a as z. So dx becomes a dz. So the integral becomes 1 by a to e dz divided by square root of 1 minus z square. That becomes sine inverse of z plus c. That becomes sine inverse of x by a plus c. So all this might seem a little bit cryptic right now, but when we start looking at applications of this in things like kinematics, etc., we'll start getting more used to it. Okay. Right now, just treat them like manipulations in mathematics. Okay, it's a little bit like algebra. They're just manipulation steps. Yeah, people, any doubt in this?
No, sir.
This clear? Yeah. Okay, so just as a final example, let's see when we apply this to definite integral, how it works out. Okay, so for example, we have something like this. We want to do integration of dx upon 9 plus x square from x equal to 0 to x equal to 3. Okay. So basically what we are trying to do here before we actually work out the integration, you can see is that if you have a function of the type y is equal to 1 upon 9 plus x square. So how this function will be looking is like, as x tends to 0, y will tend to infinity. Sorry, y will tend to 9.
Yes, sir.
And as x tends to infinity, y will tend to 0. So it will be this, okay, smoother curve, but something like this. Okay, so on both sides it's symmetrical. So some kind of curve like this. Okay, so here, and this point is 9. So 0 to 9, 0 to 3. We are just calculating this area. So at 3, you can see what the value would have become. It would have become 1 by 18. So it's so this total area we are trying to calculate. So this area is this is what we are trying to do. Now let's calculate the area and see how much it comes out to. So this can be written as dx upon 3 square plus x square. So that is 1 upon 3 tan inverse x by 3. That's the indefinite integral. So now the upper limit becomes tan inverse 1. Lower limit becomes tan inverse 0. So you know it's pi by 4. So pi by 12 becomes that area. Okay, people, so hope this is clear.
Yes, sir.
Okay, so with that, we come to a conclusion for today's class. Now, just talking about the upcoming test on Sunday, what we have discussed in today's class, the substitutions of the chain rule type and all this will not be coming in the test on Sunday. Okay, in the test on Sunday, the integration part will be only based on last week's lecture and the worksheet number 6 that I've sent you. That is simple integration formulae and properties, right? And the basic substitution of linear functions only. Okay. The remaining part of integration will be coming up in the next test, and in between we might have a DPT kind of test also related to integration to cover that portion. So for integration, the test part will be quite simple really. It will just be the basics that we've discussed in the last week and also worksheet 6 questions. Whereas for differentiation, all the applications are very important, including maxima, minima. So pay attention to that. Okay. I'll be sending you the solutions for the worksheet number 6 also, which has quite a few slightly tricky questions for maxima minima also. So make sure you revise all that before Saturday and clear your doubts if required. And that way you should be very well prepared for calculus in the upcoming test. Okay. That's it for today's session, people. Thanks for attending and wish you all the best.
Thank you,
Yes,
sir.
sir. Thank you, sir.
Thank
Bye.
you, sir. Bye, sir.
Thank you, sir.
Okay. Bye, people.
Thank you, sir. Bye, sir.
Thank you, sir. Bye.